So let's talk about Boolean algebra. And first, why do we care? So learning Boolean algebra is a lot like learning your multiplication tables. So you're going to put in a lot of effort, and it seems like it's like the super foundational, really important thing. And there's sort of all these details and all these pieces. But if you think about when was the last time you actually did long form multiplication with using all your multiplication tables and stuff? Probably years, if you're like me. And so the same thing is true of Boolean algebra. That there's a bunch of fundamentals, there's a bunch of rules, and we're going to do some of it this week. I mean, it is foundational, it is important. But the real truth is that once we have a big problem, and by big I mean more than 3 or 4 variables, so not actually that big, then we basically just give the problem to a computer. They very quickly, just like multiplication, right? In school, maybe you learn to multiply 2-digit by 2-digit numbers, and anything more than that, you give to a computer. And then we do this all the time in spreadsheets and in code and other things. So if that's the case, if we're just going to give these problems to computers instead, why waste a week of your life doing this? And the answer is it's just like multiplication. You wouldn't be able to go on if you didn't actually understand what multiplication really was, and spending some time with the details and spending some time solving some problems and working through them is part of how you develop the understanding necessary to be able to work with it once you move up to higher levels of abstraction. So in a couple weeks, we are going to start moving up and thinking it more abstractly. We're going to start using VHDL. We're going to start thinking about bigger blocks. And this foundation is ultimately going to be important. If you don't really understand what's happening at the gate level, then the rest of it will just sort of be fluffy magic and you'll just sort of, rather than having this foundation that is sturdy, you'll be just trying to pull it all together based on some rules and some inferences and some things that kind of make sense but don't quite. So in particular, Boolean algebra gives us a formal way to think about simplification and equivalent circuits. So already I think you've experienced that truth tables are really horrible for thinking about simplification of circuits directly, right? You sort of fundamentally, by definition, you can't simplify a truth table. But the whole point of it is that you write out every possible combination. Logic diagrams, likewise, or even worse, a circuit diagram is a horrible representation for simplifying things or for thinking about whether two things are equivalent. And algebra turns out to be really good for this. So usually when you are thinking about this circuit and that circuit and you want to see are they equivalent, or if I have this circuit, can I make it simpler? Or can I readjust some things or change some things such that we get the same behavior with some different desired circuit characteristics? Usually that's going to happen with some kind of Boolean equation, or more often with a set of Boolean equations, if you're doing something with multiple signals. And so as a result, Boolean algebra is, it is worth learning. Hopefully it is not too painful. And in the next little bit, I want to explain some of the identities and hopefully help make sense of this. So the textbook presents a whole bunch of theorems, kind of all at once in one big table. And here they are on one big slide. And to just take them all in at once is pretty intimidating. So I want to take just a minute to kind of break them down and help you think about them. Point out ways to kind of organize them in your mind so that hopefully they make sense. So there's sort of 4 basic categories of the way I'm thinking about it. There's the first few are sort of, at least hopefully immediately obvious from basic definitions. So the first theorem, so that any values of b and 1 is just b. So if b is 0, then the result is 0. If b is 1, the result is 1. So it's always just b, whatever that is. The second one, b and 0 is 0. So anything and 0 is always going to be 0 by definition. And b with itself, so if b is 1, then both of these, of course, are 1, which is just b. And if b is 0, then both of these are 0, which again is just b. So these 3 hopefully fall out immediately from the definition. Okay, and then number 4 and number 5. So number 4 says if we invert something twice, we get back the original thing. So this just falls straight out of having only 2 values that we're working with. So if we invert 0 and we get a 1, we invert it again, we have to go back to 0. And the same if we started with 1. And number 5 just says that if I have b and not b, then that always has to be 0, because either b is 0 or not b is 0. And so one of these two things must be 0, and therefore the result is 0. And conversely, if you're ORing them, one of these two things is going to be 1. So either b is 1 or b is 0, in which case not b is 1, and so the result will be 1. So again, hopefully all of those sort of just fall out of the basic definitions of how we've defined Boolean algebra and are not too hard to comprehend and not too hard to use kind of immediately. Okay, then we've got a second set of things, numbers 6, 7, and 8, that are very similar to things you've seen in algebra. So number 6 just says that both and or are commutative. So I could flip the values around. So if I have b and c, it's the same as c and b, or the b or c is the same as c or b. So this is just like multiplication or addition in algebra. And again, that's part of why we're using the dots and the plus signs, because it behaves much like multiplication and addition. Similarly, it's associative, so I can take b and c and then and that with d. And that would be the same as if I took c and d and then anded that with that thing with b later. So I can group subgroups of a number of things being anded, or over here a number of things being ORed together as well. Okay, and then finally number 8 is what in algebra we call distributivity. So if I have a b outside, so b and c or d, I can push the b inside, so I end up with b and c or b and d. This is just like being able to factor the common factor out of a larger sum. So again, the thing that's a little different than algebra is that both and or can be distributed over each other. So unlike algebra, where it only goes one way, in Boolean algebra, it can work both and or can be distributed over each other. So you can factor out the b here, but you can also factor the b out of this product as well. Okay, so that's rules 6, 7, and 8 that are a lot like algebra. Then there are rules 9, 10, and 11, which can be derived from the following, or from the rules that we started with so far. And frankly, it's not worth your time to spend a lot of time studying and memorizing these, or even necessarily deeply understanding them. If you need them, you can always go back to the book and figure them out. But in practice, generally, they're going to come from other theorems above. And once we start doing Carnot maps, that's usually a way better way to think about what's going on here than trying to make your brain do the mental contortions to do these particular theorems. And then finally, we end up with De Morgan's theorem, which is number 12. And this one is super important. So I'm going to take a few minutes in the next video to talk about that one. Okay, so like, what do I need to remember? Like, what's really the key stuff here? And I think remember is the wrong thing. So it's like, cross that out. What really do you need to be able to use is the important thing. And the answer to what do you need to be able to use are the axioms of Boolean algebra, so that we have 1 and 0, and that 1 is not 0, and so forth. And then theorems 1 through 8 from the previous slide, and De Morgan's theorem number 12. So like I said, don't bother with number 9 through 11. Either your algebraic simplification will already handle them, or you really should be using a K-map or just using a computer to solve it. Don't make your brain hurt trying to use those. And so hopefully that helps break it down a little bit. These rules are worth getting familiar with, but it's not important that you memorize them all or be able to recite them or remember which one is associativity and which one is distributivity or whatever. That's not particularly relevant. So hopefully that much like if you had a table of trigonometric identities, that you could use that table while you were solving problems effectively. That's really what I want for you out of this.